Because hydrogen ion concentration can change quite rapidly with high-intensity exercise, the body requires a way to very quickly be able to respond. In this case, the body is able to rely on buffers as a way to regulate hydrogen ion concentration. A buffer resists pH changes by removing hydrogen ions when the hydrogen ion concentration increases. A buffer will release hydrogen ions when the hydrogen ion concentration decreases. We have both intracellular and extracellular buffers, and our intracellular buffers work as our first line of defense in stabilizing our pH within our muscle. Within the muscle, we have bicarbonate, which is a useful buffer during exercise. We also have phosphate buffers, which play an important role at the very onset of exercise in stabilizing hydrogen concentrations. Numerous proteins that contain histidine or histidine dipeptides are able to bind with free hydrogen ions to maintain pH within the muscle. There are three primary extracellular buffers, again bicarbonate, hemoglobin, as well as blood proteins. Blood proteins are found in very small quantities, thus their usefulness as a buffer is going to be relatively limited. So instead, we're going to rely primarily on bicarbonate as well as hemoglobin. Hemoglobin serves as a primary buffering capacity because it has a very high affinity to bind with hydrogen ions after it is not bound to oxygen any longer. So it's going to work really well to help us remove hydrogen ions from the blood. The bicarbonate buffer system is by far our most important buffering system that we have in the muscle as well as in the blood, so both an intracellular and an extracellular mechanism in this case. Importantly, it involves carbonic acid, H2CO3, which undergoes the following dissociation reaction to form bicarbonate, which is HCO3. And that will also then undergo a conversion to H2O and CO2 by the time that the carbon dioxide reaches the lungs. Now, if you want to control for the math of how this actually happens, when, in this case, we know if we're moving left or right in this equation, because importantly, you can see that the arrows go in both directions, that is actually determined by what is called the Henderson-Hasselbalch equation. And based on the proportion of CO2 and the proportion of hydrogen, it'll push the equation one way or the other. So if you have a very high amount of CO2, it'll force the equation to the right, producing hydrogen ions. If you have a high amount of hydrogen ions and a low amount of CO2, it'll force the equation to the left. So we tend to have high CO2 production in the muscle, so it's going to force the equation to the right. And then we have low CO2 in the lungs, so it's going to force that equation, in that case, to the left. It's important that we're able to move hydrogen ions from inside the muscle into the bloodstream or interstitial space, and vice versa. And we have two primary mechanisms by which we can do that for skeletal muscle transporters. First, we have the sodium hydrogen exchanger, or NHE, and it's going to move one sodium molecule into the muscle fiber in exchange for transporting one hydrogen molecule out of the muscle fiber. We also have the monocarboxylate transporters, or the MCTs, and these work as co-transporters. So one lactate molecule and one hydrogen molecule are moved out of the muscle fiber, and there is no exchange of having to move something into the muscle fiber in this case. So I want you to stop and think, where else in the body might you find those NHE transporters, specifically the ones that are moving one sodium in and one hydrogen out of the cell? In this case, we're talking about muscle, but there's got to be somewhere else in the body that might be efficacious. Take a moment and jot down your answer. If you chose the gut, then you're correct. That's another area in the body where we have high levels of acidity, and we might need to adjust that acidity at times. And so in this case, we can use those same NHE transporters to move hydrogen out of the stomach and to move sodium into the stomach. For a long time, athletes have been using dietary supplements in an effort to maximize exercise performance, specifically sodium buffers. And the idea here is that using sodium bicarbonate, would induce an alkalosis by increasing the bicarbonate pool and the pH, which would give you a wider window with which you could manipulate hydrogen ions before it would become too acidic and cause performance deficits in the muscle. The other alternative is sodium citrate, and that was introduced as an alternative to sodium bicarbonate, primarily because people thought that it would elicit less gastrointestinal issues, which is one of the primary issues with sodium bicarbonate. However, we found that studying these alkalizing agents, both sodium bicarbonate and sodium citrate, is challenging, and there's a lot of inconsistencies in the literature as far as how they influence performance. Even more recently, there are products that are currently on the market that function as a lotion that you can actually rub on your legs before exercise performance or on your arms, depending on what the activity is, in order to absorb that through the skin right into the muscle to act as a buffer. And these are really popular right now in both the cycling as well as the running community, even though the literature is really kind of split on how efficacious those products are. So you might be wondering, how do those elite level athletes continually do repeated bouts of high intensity exercise and they don't seem to fatigue? I know that when I do those exercises, I fatigue relatively quickly. Well, one mechanism is that first, type 2 fibers are better able to handle high amounts of hydrogen ions compared with type 1 fibers. So they're better able to excrete those hydrogen ions and maintain pH within the muscle. But also importantly, with training, specifically anaerobic style training, we get improvements in our ability to maintain hydrogen balance. So we're better able to move hydrogen out of a muscle cell in this case. So when you think about those elite level athletes, someone who's able to be explosive time after time, a lot of that is actually a training adaptation to those hydrogen and carnosine transporters that they have within their muscle. It's important to review how the respiratory system has an influence on acid-base balance. Whenever you're doing exercise, you're increasing ventilation. And importantly, this is causing CO2 to be blown off in the lungs. And this will raise pH or make it more basic. And this is helpful because it's going to shift our equation to the left to remove hydrogen ions in the body. And if you think about your ventilation during exercise, when it's low intensity, your ventilation is low because you're not producing a lot of hydrogen ions, nor do you need as much oxygen getting to your tissues. At high intensity exercise, it is significantly higher, which is not only helping bringing oxygen in, but also getting rid of those hydrogen ions. Keep in mind that the kidneys are one of our chronic ways to control hydrogen ions in the muscle. So they're not going to be one of those acute or very fast responses in controlling pH within the muscle. Specifically, the kidneys function to either excrete or not excrete bicarbonate, which is one of our buffers for hydrogen ions. Whenever the pH is very low, meaning we have a high amount of hydrogen ions, the kidneys are going to not excrete bicarbonate, keeping it available to bind those hydrogen ions in order to lower the pH of the muscle. But whenever we have a high pH or a low amount of hydrogen ions, the kidneys will excrete extra bicarbonate that exists. Hydrogen production will depend on three things, primarily on exercise intensity, but also the amount of muscle mass involved. So the more muscle mass, the more potential for hydrogen ion production, as well as duration. So the longer at the activity at high intensity, the more likely that hydrogen ions are going to be produced. An important concept from this slide, if you take a look at the figures on my left, is the fact that muscle pH will change more rapidly than blood pH. And this makes sense since the hydrogen ions are actually being produced in the muscle and they have to be transported out into the blood. So anytime you take blood sampling from the body, know that that is a delayed response from what's actually happening within the muscle. So to wrap up, let's put some percentages to how much each of these buffers are contributing to controlling hydrogen ions. When we're thinking about in the muscle, so intracellular, our proteins play the largest role, with the next largest role being played by bicarbonate and those phosphate groups having very small roles. When we then look at what's going on in the blood or extracellular, this is where bicarbonate shines and is the primary buffer. And we get a minor bit of help from hemoglobin as well as blood proteins.